welcome to RF transceiver design course. We are discussing the transceiver architecture in last class. We will continue with the transceiver architecture. In last class we have seen the heterodyne receiver. We have also seen the various what are the aim of receiver design. Now we will move forward for other architecture. So, last class we have stopped at sliding IF architecture. So, here in this example your FIF is equal to F1 by 3. So, here F1 F2 let us say if you have a multiple frequency with certain bandwidth, this is F1, this is, then there is a F2. So, this F1 F2 will be considered based on the bandwidth of the signal, and the F2 plus F1 by 2 is a center frequency. So, we can write bandwidth, this is called a fractional bandwidth delta omega by omega naught. So, this is how when we consider the sliding IF architecture, the bandwidth of IF should match with bandwidth of RF, so that the same information we can down convert at the baseband. Now, we will move to the next architecture, that is a. So, before moving to the another architecture for super heterodyne receiver, there is a LO planning which is important. So, we will see what are the if we try to choose some LO frequency which is multiple of LO1, or if we try to choose some other LO frequency, we should keep these 2-3 things in mind before going for the other architecture. So, let us discuss about the LO planning in super heterodyne receiver. So, whenever you are trying to design a super heterodyne receiver, you need to carefully plan the LO frequency. So, as we know that in super heterodyne you require a 2 times down conversion. So, we are using a 2 mixers. So, you need a 2 separate VCO or synthesizer or PLL that can be incorporated because you have a separate LO frequency, and the IF LO, your one of the IF is a fixed, and the RF LO is variable to down convert the desired channel to pass band of the IF filter. So, IF filter generally SAW filter is used, that is a surface acoustic wave filter which will give the sharp rejection. And we have seen in the last class that you need multiple filters and multiple mixers combination. So, this will generally be a 3-4 chip solution, it cannot be accommodated in the single chip. So, and you have many off chip components also will be there. So, whenever you are trying to implement the super heterodyne receiver, it will be little bit the complete setup will be bigger in size, and it has a many off chip components are also involved. Now, LO1, whenever we try to find out the frequency LO1, so this LO1 should never be close, this LO1 should never be close to integer multiple of LO2, because our LO1 will always be higher than LO2. So, LO1 should not be integer multiple of LO2 for any channel, and the nth harmonic of the fixed LO2 could leak into the RF mixer and cause unwanted mixing. So, here the one good example is given. So, this is LO1, and this if LO1 should never be close to integer multiple of LO2. So, this LO2 is a lesser. So, if there is a n times LO2 if we consider, and that LO2 and there is some unwanted signal which is at higher frequencies. This is a desired signal. So, this is a desired signal, and then this is a multiple n multiple of LO2. Now, because of the n multiple of LO2, at same higher frequency, if some image is there, then what will happen, that this will also be down converted to the baseband. So, we need to be careful that while choosing the LO frequency, the LO1 should never be close to an integer multiple of LO2 for any channel. So, otherwise the image will be also down converted due to the amplitude of LO2. So, that needs to be, while finding out the LO, means while planning the LO frequency for superheterodyne, this we need to be careful. Another problem in the LO is a half IF problem. So, if there is a IF frequency, this is a IF frequency, and then there is a half IF, at the half IF there is a image. So, if we assume that there is a blocker at halfway between the LO and desired channel, so due to second order non-linearity, so here if we try to consider the second order non-linearity, so your M blocker T, which is cos omega LO plus omega F T square, and then if we square this term, then what will happen, you will have a 2 omega LO frequency will be there. Now, this 2 omega LO with this blocker, because this is at half IF, but if this LO is a double, then you will have the component. So, if the LO has a second order component, then this signal will fold right on the top of the desired signal. So, 2 omega LO plus omega F into cos 2 omega LO. So, this is a IF frequency, and it will directly come at the baseband. So, because your LO is multiplied by 2 and you have a image here, that is why you will have this, let us say if this is twice of this, then it will be down converted. So, we need to be careful while deciding the LO frequency, that it should, if there is any image is coming in between, or any desired is, if there is any application where let us say when you are finding out the frequency of LO frequency, and if IF is lying somewhere at the desired GSM band or ISM band, then we need to be careful. We need to avoid that LO. We have already seen in the last class, in that example where we have discussed the sliding IF, where there also there is a problem of the half IF and half IF problem. Another problem, if the IF stage has a strong second order non-linearity. So, if there is a very high non-linearity in your system, and moreover there is a second order non-linearity, then half IF problem occurs through the non-linearity mechanism, because this M blocker cos half omega F will be squared, and then you will have a twice of omega F. So, this will directly be down converted at the baseband. So, we need to be careful while considering the any receiver component, it should not have the second order nonlinearity. That is why for while designing the low noise amplifier also, second order nonlinearity is important, and this highlights the importance of frequency planning. And one should select the IF by making sure that there is a no strong half IF blocker. There is a no strong half IF blocker. There should not be any strong half IF blocker. And if there is a something exists, then the second order nonlinearity must be carefully managed. So, always when we try to do the planning, LO planning, we need to be careful that we should not have the half IF blocker in between the frequency that we have decided, and the LO is not multiple of LO2. So, that needs to be careful while considering the heterodyne receiver architecture and when we do the LO planning. So, if we noted down the disadvantages and advantages of heterodyne architecture, it require off chip SAW filters which will reject the image also, or for band selection also, and 2 synthesizer are required, 2 PLLs or synthesizer, and it is generally 3 chip solution where RF, IF and synthesizer will be there. What are the advantages? It is a robust. So, there are many critical let us say mission mostly for satellite application, or when you have sent your rovers to the Mars or Moon and you want your you want accuracy. At that time we need to consider that your signal will not fail. So, by at that time we should be careful of designing the architecture, deciding the architecture, so that our performance will be robust. So, the clear choice for extremely high sensitive radios or high dynamic range SAW filters reduces and relaxes the burden on active circuits, and this makes it much easier to design an active circuitry. So, if we try to reduce the SAW filters, then we can have a more we can reduce the number of chip solution in this heterodyne architecture, and we can have a lower power consumption because we have many passive components like SAW filters in the means if we consider in terms of the number of off chip component, passive component, it is a power consumption is low, but it is not sufficient low compared to other receiver architecture like direct conversion receiver. Now, we will move to the next architecture, that is a 0 IF receiver. And what are the properties of 0 IF receiver? We already have seen for 0 IF receiver while discussing the sliding IF that your omega RF is equal to omega LO. Because your omega RF is equal to omega LO, you do not have the problem of the image. So, the merits is the absence of image greatly simplifies the design process. There is no image, and channel selection is performed just by a low pass filter and we can implement on chip. So, this complete solution can be made on chip. There is not a single component that we can keep off chip. Without off chip component, we can make a complete 0 IF receiver. And mixing spurs, as we have seen, because in heterodyne there are 2 LOs. So, there is a plus or minus M LO1 plus or minus N LO2, and this is a omega input frequency. So, this many spurs can be reduced because here you are directly down converting and there is only one LO involved. But it has a merits, it has a demerits also that we will try to see in the in upcoming slides. What are the first demerit of the 0 IF receiver is a LO leakage. So, what will happen if this is a local oscillator and if this is a mixer, and if we consider the mixer is not ideal mixer, it has a non ideality, it is made by using MOSFET or BJT. It has a certain capacitance between output and input which limits its performance at high frequency, and if there is a feed through, means the signal which will be fed back, then the signal is going back to the low noise amplifier. Again, low noise amplifier isolation is not sufficient, means output to S12 is not sufficient enough, then the signal will again go back to the antenna. So, there is a LO leakage will occur towards the input, and if this LO leakage will occur towards the input, there is a possibility same LO frequency will come back and you will have a problem for the when you have a second order or third order nonlinearity, and that needs to be considered. Now how can we solve this problem? The easiest way to solve this problem to consider the differential architecture. So if there is a differential fully differential architecture of LNA mixers and all other components, then you can because this is a common mode signal and it can be easily cancel out. But we need to add a fully differential architecture which will increase the power consumption. So, and you also need to have the belen at the input side to convert single ended signal to differential signal, because your antenna is a single ended. So, this is a one of the demerits of direct conversion. So, this 0 IF receiver has a, it can be called as a direct conversion also. So, it is a 3 name. One is direct conversion, one is a 0 IF, another is a direct conversion. It is also known as a homodyne. It is also known as a homodyne receiver. So, because we have seen a heterodyne, this is called homodyne or direct conversion or a 0 IF receiver. Another problem of this is a DC offset. So, if there is a antenna and it is connected through the pad, this is a chip. So, this is if entire thing is on chip, and these are the pads of the chip. If this entire is a on chip solution, and this has a pad, it has connected through PCB through antenna, and if there is some signal, we already have seen if there is a leakage of some LO signal and that will be feedback, then you will have a sufficient DC offset, and that DC offset is very high. We need to be careful while designing the circuit, while designing the direct conversion receiver. So, we can take an example here that your receiver, if your receiver sensitivity is a minus 80 dBm, let us say this is a sensitivity that we are targeting, the total gain is given by the 80 dB. So, because we want at least 0 dBm signal, so that ADC has a sufficient amplitude to convert to the digital. So, that is a 80 dB gain if we have added, and if your output desired power is 0 dBm. Now, for example, if there is a, because LO power is sufficiently high, if there is a leakage, if there is a only 40 dB isolation here and 20 dB isolation here, and if there is a leakage of LO, and that leakage of LO is around minus 60 dBm, what will happen, that your receiver gain is fixed, that is 80 dB, minus 60 dB is coming, and same omega LO frequencies is same. Then because omega LO when it is multiplied, you will have a DC offset generated, that will be in the range of 20 dBm. So, this is a very high amplitude and it might distort the other IF components, IF amplifier or other components which are coming after the mixer. So, this we need to be careful while designing the direct conversion receiver, and this is a there are many publications you will find that how to overcome the problem of DC offset. So, there is one way we can overcome the problem of DC offset, that is by using a high pass filter. So, this is a high pass filter. if we introduce, and then if it is a sharp enough f1 and this minus f1 will should be decided based on the R1 C1. But the problem is in we have already discussed while discussing the basic of wireless communication, the information of the modulated signal is lying in the around the 0 frequency. There are more information will be there around the 0. So, if we reject the 0, if we try to reduce the 0, there is a possibility that we lose the information. So, there are some active DC offset cancelling technique can also be employed. There are various techniques can be used to remove this DC offset, but this is a very significant problem for direct conversion receiver. Then there is the problem of even order distortion. So, in even order distortion, we already have seen one problem of if there is a half IF, if there is a half IF issue, if there is a blocker at the half IF frequency, then also you will have the second order might create a problem. There is another we can say another problem if the two tone, this is omega 1, let us say this is a spectrum and this is omega 1 and omega 2, and then this difference of these two omega 1 minus omega 2, because this is at very high frequency, but this is coming to the antenna and our receiver, this omega 1 and omega 2, if you subtract omega 1 minus omega 2, then this when it is applied to the our receiver which has a not good second order linearity, then it might fall this omega 1 minus omega 2 might fall near to the your desired frequency or desired components. So, here this omega 1 minus omega 2 is happening because of the blocker which is too far, and there is a second order non-linearity. I already when we discussed the non-linearity, I already told that if this is m omega 1 plus or minus n omega 2, and if we want to know that it is a first order, second order, third order, we should write m plus n. So, here m plus n 1 plus 1 which is equal to 2. So, that is why this is a second order non-linearity. So, the problem of even order distortion is critical enough to merit the quantitative measure, and this is called as a second order intercept point IIP2. This is mentioned as a IIP2 second order intercept point, input intercept point which is a second order, and this can be measured by two tone analysis. However, the frequency of interest is a beat component. So, we should apply a two tone which will make a beat frequency omega 1 minus omega 2 near to the desired band. So, you can plot the second order non-linearity. So, if there is a signal which is first order, so this is a alpha 1 A, this is a first order, and then this is a second order. The only difference in this is the slope of this is a 2 times n slope of this. So, this is a single time and this is a 2 time slopes. So, this slope at one point of time when you extrapolate this point, it will intersect at one point, and that point is called AIIP2, and at output it is AOIIP2. So, K alpha 2 AIIP2 square, the point at which both will intersect, K alpha 2 A square IIP2 which is equal to alpha 1 AIIP2, you will get AIIP2 which is somewhere 1 by K alpha 1 by alpha 2. So, you can easily plot you can easily find out the IIP2 of any system by applying the two tone and considering the beat component or the second order component omega 1 minus omega 2 which is near to your desired frequency. So, we already have seen 3 demerits. One is a problem of LO leakage, second is a DC offset, and third is a problem we need to be careful in even order uh, distortion, and the fourth is a flicker noise. Because we are directly down converting the 0 frequency, the complete receiver chain or even the mixer has a very high flicker noise has been seen. Because and flicker noise we already discussed while discussing the noise is dominant at low frequency, and here you are down converting frequency at 0 frequency. So, this flicker noise is a significantly high, and that can be mentioned on the log scale. This is a corner frequency, and what is a corner frequency? I already told. Corner frequency is nothing but frequency at which your thermal noise equal to the flicker noise. But if your IF range is below the corner frequency, or if this is a bandwidth by this point is called bandwidth by 1000, if it can be mentioned, then there is a very high noise, and we need to get rid of this flicker noise. That is important while designing the direct conversion receiver architecture. So, flicker noise is also significant when we design the direct conversion receiver architecture. Another problem is a IQ mismatch. So, because I already told that when direct conversion receiver we design, we use a quadrature demodulation or quadrature down conversion. So, in the quadrature down conversion, you have a this is a LO frequency, and then you apply the sin omega LO and cos omega LO. So, this if there is a if there is a I and Q has a mismatch, how this mismatch will occur? The mismatch will occur in the phase and gain. So, there is a mismatch will be there due to the phase and gain error. Let us say there is some mismatch in the phase of the sin and cos, and that will create the change. So, this is a black which is the desired one, and the red which is due to the mismatch. So, there are two kinds of mismatch is possible. One is a amplitude mismatch and another is a phase mismatch. So, if here there is a amplitude mismatch is shown, if there is a phase mismatch also, the your constellation diagram, we already have seen what is a constellation diagram while discussing the wireless basic of wireless communication. So, here this is the ideal constellation point, and due to the change in the amplitude it is shifted to the other point. So, its amplitude has been changed. If there is a mismatch in the phase, so there is a possibility that you will have some your this will something look like this. So, this your constellation will change, and due to the phase it might change the it will be more angular, and we while we see the down converted signal or baseband data, you will see the significant difference in your constellation diagram if there is a sufficient IQ mismatch. So, we need to avoid the IQ mismatch as much we can. Then the problem of mixing spurs, here there is a because there are not so much mixing spurs like the heterodyne, but still there are a issue that LO harmonic does manifests itself if the receiver is designed for wide frequency band. So, if there is a wide frequency band and greater than 2 octaves, for example software defined radio or cognitive radio, where we want to have a radio which is changed, at that time we change the LO frequency wide enough, and due to that there are more mixing spurs, because LO frequency has a multiple harmonics n LO n omega LO, and that will there is a problem of mixing spurs will also observed in the direct conversion receiver architecture. So, these are the points, these are the merits of the direct conversion, demerits of the direct conversion receiver. The merits we already have seen, there is a problem of IF is solved, the problem of problem of image is solved, the problem of multiple chip solution instead of that single chip solution is possible. We can easily filter out and select the channel. So, this is how the direct conversion is benefited. However, it come with the demerits also. The demerits we have seen, that is a leaky LO leakage, then there is a problem of DC offset, there is a problem of flicker noise, a IQ mismatch, mixing spurs. So, all these problems are also there while designing the direct conversion receiver. So, we need to be careful while designing, and we need to consider all these demerits also. We will discuss about more receiver architecture in the next class. Thank you.